All right, it's time for review block number 2. If you look at your final fortnight's document, you can see that we're going to talk about forces, Newton's laws, equilibrium, gravity, and all the way up through projectiles. So let's get started. First of all, a force is a push or a pull. That's it, measured in newtons. And of course, a newton is a kilogram meter over second squared. And you can't talk forces without talking Newton's 3 laws, which is the backbone of dynamics. Newton's first law has a goofy name. It's called the law of inertia. And for testing purposes, inertia is the same thing as mass. So don't be confused by velocity being thrown into a problem. The object with the most mass has the most inertia. What does the first law say? Well, basically, objects at rest remain at rest. That's not complicated. The slightly harder part is objects in motion remain in motion, constant speed, straight line. And I skipped the unless part, but unless acted upon by an external unbalanced force, which we tend to call a net force. Now, this is hard because it might be somewhere in the depths of your brain that in order to keep moving, an object needs a force on it, which is not true. An object may need a force on it to get moving, but once it's moving, if you remove all forces, the object will just continue constant speed, straight line. Newton's second law is by far the most important of his laws. In my opinion, F net equals ma. Net forces cause an object to accelerate, not just a force, but a net force. Remember, we need a free body diagram to determine our net force, but all net forces lead to acceleration. And then the important concept of equilibrium. An object is in equilibrium when there is no net force acting on the object. Now, this needs to be true, or can be true in the x direction, and it can be true in the y direction, or both or neither. But typically, we're looking at the x direction to see if an object is accelerating or not in Regents Physics. So if F net is 0, the object's in equilibrium. And then finally, the law that everyone can recite but nobody actually believes. That would be the law of action-reaction. For every action, or force, there is an equal and opposite reaction, or force. Now, the reason that one's so hard to believe is we somewhere, again, in the depths of our brain, we want to believe that when a baseball bat hits a baseball, that the bat exerted a larger force on the ball than the ball did on the bat, which is not true, of course. Anytime two objects are pushing or pulling on each other, the forces are going to be the same. Now, why do we see drastic results, like the bat doesn't slow down much, but the ball gains a whole lot of speed? Well, that's because of a difference in mass. The forces were the same, but because of the drastic mass difference, our eye observes different accelerations, which tricks us into thinking the forces are different, but they're not. Anytime two objects pull or push on each other, the forces are the same. All right, weight versus mass. A common confusion in the course is the difference between the two. And of course, our equation, which is on the reference table, solved for little g. Little g equals Fg over m, where Fg has two names, the force due to gravity, or weight. Now the weight, let's pick red here to write in. The weight is measured in newtons, whereas the mass is measured in kilograms. And let's equate those. And of course, little g is measured in meters per second per second. So as I mentioned earlier, a newton is the same thing as a kilogram meter per second per second. And the normal force, which of course plays a role when we get to friction, the normal force is the table pushing back, or a surface pushing back. If an object is sitting on a surface, well, then the surface will push typically upward with a force equal to the weight. For Regents Physics, what you need to know, it's not always true, but in Regents Physics, introductory physics, the normal force and the weight are the same. Now, this should all remind you of the problems we've been working all year. The box sitting on a horizontal surface, forces acting on it, and then, of course, a multi-step problem. So why don't you put the video on pause and work this problem out, and then we'll go over the solution. All right, hopefully you hit pause and put the time in and did the problem. If you did, here's what you should have gotten as answers. The weight, which you should have used Fg equals mg. This is why we don't say the word gravity in Regents Physics. This is the force of gravity, and this is the acceleration due to gravity, but the word gravity is not enough. When you put in 3 kilograms, you will get 29.43 newtons. And of course, if it's sitting on a horizontal surface, the normal force will be the same as the weight, 29.43 newtons. I like to label with both the variable name, or the force name, and the actual value. And then we had a pulling force to the left of 28 newtons and a force of friction to the right of 7 newtons. That's our big four, the forces that typically all occur in our free body diagram problems. If the surface was frictionless, we'd be missing this 7 Newton force to the right, but it's not. Then you had to determine the net force. The temptation is to want to use F net equals ma, but you don't know A. If you know the left force and the right force, you could determine the net force simply by subtracting them. So our net force here will be 21 newtons to the left. And the third part was to find the acceleration of the object. Acceleration is F net over m, right? Newton's second law. And here's your F net and your mass of 3 kilograms, giving us an acceleration of 7 meters per second per second. And the last part, I know we didn't review friction, but here we go. The last part is to find the coefficient of friction, not the force of friction. We already know the force of friction. So the equation that you would use straight off the reference table is the force of friction equals the coefficient of friction times the normal force. And we've already found the normal force is 29.43 newtons. That's what you would put in there. And we know the force of friction is 7 newtons. That's what you would put in there. And you would divide FF divided by Fn. And that will give you the coefficient of friction. Remember, since you're taking a force and dividing by a force, the units are going to be newtons over newtons, which is nothing. There are 2 numbers in the course without units. That would be coefficient of friction and index of refraction when we get to waves. All right, slide 5. Universal gravitation. This is whenever 2 masses are pulling or pushing on each other, actually pulling on each other. The Newton's law of gravity, which applies to every 2 masses in the universe. Remember, you are currently pulling on everything in the universe with a force that is equal to capital G, right here. That's on the front page of your reference table, including units. Capital G times mass number 1 in kilograms times mass number 2 in kilograms divided by, this is not radius squared, this is distance between the centers squared. And when you're all done, you will get a force that is measured in newtons. And because we have r squared downstairs, when you go to graph y versus x, and your x is downstairs in the denominator and squared, hopefully you remember what the graph looks like. We've been doing it all year. The graph will be a hyperbola. It's the steep version of hyperbola because we have the r squared in the denominator. Now, proportional reasoning. That's the game we've been playing where you double this, triple that, and you decide how much bigger or smaller your answer actually is. So let's switch over to some Ballston Spa purple here. And why don't we double the distance between the objects? If we double the distance between the objects, what will happen to our gravitational force? Well, the temptation is to say it'll be half because I have to put an extra 2 here in the denominator next to the distance variable. But notice that the r is squared. So whatever happens to the r also happens to the 2. So if you double the distance between the masses, you will have 1/4 the force of gravity that you used to have before. Gravitational field strength, well, let's see. Your gravitational field strength is little g. If you look at your reference table, little g has 2 names, gravitational field strength and acceleration due to gravity. If you encounter a problem where they're asking you for gravitational field strength, they're really just asking you for that same old little g. So solve for little g and put in the weight and the mass, and there you have it. All right, projectiles. We are going to talk about horizontal projectiles and then briefly projectiles at an angle. And remember, probably the most important thing you can remember about horizontal projectiles is it really is just a fancy dropping problem. We've got our red pencil back here. It's just a drop, which means if you launch an object horizontally off a cliff, the object, when it leaves the edge of the cliff, will hit the ground in the same time as a dropped object, which is at first hard to believe, but when you see it and you think about the physics of it, I mean, the falling aspect, the little g equals 9.81 meters per second, doesn't really care about the fact that the object is moving in the x direction. So, how do we analyze a horizontal projectile? Well, we look at the x motion separately from the y motion for a very good reason. The x direction is constant speed motion, which means when you're doing x motion, you need only the x equation, which is equation 1 on the reference table, which would be the v bar equals d over t. That's the only equation you want to use when working a horizontal problem, because there is no acceleration in the x direction. Now, in the y direction, the actual falling aspect of it, probably the most important thing to remember is that your initial y velocity is 0, because you are not moving in the y direction, you are only moving in the x direction. Now, that's only true upon departure from the cliff. After that, of course, the object will gain speed in the y direction. So if you're working a y direction problem, because of gravity, you're working a constant acceleration problem. So what do you use? Well, you may use equations 2 through 5 on the reference table. Now, typically in reality, this just turns out to be a two-step problem, your typical horizontal projectile. The first thing, if you know the height of the cliff, you would want to find the time of flight. And the time of flight is typically found with d equals vit plus 1/2 at squared, where the a is actually a g, and there is no initial velocity in the y direction. So, as has happened all year long, when you solve that for time, you're going to get t equals the square root of 2d over g. And then once you have that time, you plug it into v bar equals d over t to solve for d. That's your typical two-stepper. Why don't you pause the video and try to work out the solutions. Height of 75 meters, Vx of 35 meters per second. All right. Hopefully you put in the time to find these answers. If you actually do, t equals the square root of 2d. Now, it's important to keep in mind that that d is actually the dy. It's the height of the cliff over the acceleration due to gravity. You should be getting 3.91 seconds. And then you plug that into our v bar equals d over t, or d equals v bar t. You should get about 137 meters, or 136.85. All right, projectiles at an angle. Really, they're not much different. There's still two separate problems happening. You have an x problem and a y problem. You're typically going to be given a launch speed and an angle of launch. This is usually above the horizontal, so this right here would be our 50 degrees. And the first step, usually, is to find the components. We have to find our components because you don't want to use the 40 meters per second for anything because it's pointing in both the x and the y direction. You don't want to use it for anything other than to find the components. This v of 40 meters per second is what would go in for both v's here in the x and y components. Now, this is the ax equals a cosine theta and ay equals a sine theta that you can see on your reference table. That's equations 6 and 7. And you could use this, of course, for forces as well, which we did during the year. But here we're going to use it for velocities. So you're going to find the x component of the velocity, vx, and you're going to find the y component of the velocity, vy. That's not a very straight arrow. And that would get you started on the problem. And then Once you have the x and the y, then you don't ever look at this v of 40 meters per second again. Everything you put into your equations is going to be either the x or the y velocities. And what do? We find the time of flight, and the time of flight is typically found using, well, it's definitely found using the y direction, and it's going to be using one of your equations that has a t in it in equations 2 through 5. And just like before, dx will be vxt, and dy, again, you can use any equation that has a d in it for the y direction. Typically, we'll use our d equals vit plus 1/2 gt squared. Now, vi is not 0 anymore. Of course, you have an initial y velocity. So why don't you put it on pause and go ahead and step through finding the time of flight, the dx and the dy, and we'll see how you did. All right. Let's see how we did. Our answers, if you put in the 40 meters per second and the 50 degrees, you should have gotten an x component of 25.7 meters per second, a y component of 30.6. And when you find the time of flight, typically Vy final, which is going to be 0 up at the peak, right? When this projectile follows its parabolic trajectory, which will look like that. Up here at the peak, you still have your x velocity. That never goes away, right? The x speed is constant, but your Vy final is 0 here. So when you put in a 0, your Vy initial is going to be whatever your y component was. And when you do this, you're only finding the time to the peak. Of course, you have to double it. So doubling our time to the peak, 6.24 seconds. And dx, again, we can only use v bar equals d over t in the x direction. You should have gotten 136.85. And your dy, 47.7 meters. Actually, this is not true. That's a copy and paste error from the last problem. The dx is going to be vx, which is the 25.7 times the 6.24, which is about 160.4 meters. Sorry about that. 160.4 meters. And your dy will be vit. Of course, the vi is the 30.6 meters per second. Now, it's important to remember that in this equation, for the x direction, because it takes the full time, that we put the full time in here, but to find the maximum height of the projectile, which is your dy right here, that occurs at the half time. So both times that you put in have to be the half time, the one before you doubled it, the 3.12 seconds. So when you put all that in, and of course this is actually little g of negative 9.81 meters per second, right? This is not a dropping problem. And you should get 47.7 meters. All right, last slide, a couple of qualitative things about projectiles. Maximum range, that is the dx value. A projectile will go the furthest, hopefully you remember, when launched at 45 degrees. And if you want the projectile to go as high as possible, the maximum dy, well, you would just fire it straight up. You would fire it at a 90-degree angle. Now, it would have no dx if you did that, but it would have the maximum dy. And, of course, that would also give it the maximum time of flight. You would also fire it at 90 degrees straight up. That would give it the maximum time. That's because the y component of the launch, the Vy initial, the one that uses the sign, that is what determines the time of flight. So the bigger the y component initially, the bigger the height. So the y component is the biggest when launched at 90 degrees. And here's just a fun fact. Complementary angles have the same range. So if you launch a projectile at 10 degrees or 80 degrees, since they add to 90, the dx for both of those projectiles would be the same. And finally, air resistance ruins everything. If you fire a projectile and there's actual air in the room, because everything we've discussed assumes no air resistance, then it would go less high and it would go less far.